And has worked for a number of companies, focused primarily on the interpretation of indicator minerals in the Kalahari environment. And as for Herb Helmstead, I'm sure most of the people here on the call know Herb very well. He is one of the foremost researchers on mantle tectonics from Queen's University out of Canada. And so with that, no further ado, Andy, you're going to talk to us about the evidence for a megacryst origin of the Cullinan and other big type 2 diamonds. We look forward to your talk.
Thanks, Tanya. So this talk is about the high value type 2 diamonds, and we're going to suggest how they formed and also discuss ways that you can try and decide whether kimberlites might have these type 2 diamonds, which obviously has important economic application. We're not there yet, but we think we've got pointers as to the way that we need to go. Oh, no. For some reason. Sorry. Okay. Just to get some of the jargon out of the way, diamonds are divided into two broad groups. One has nitrogen impurities, which gives the diamonds a yellow color. These are type 1 diamonds. Type 2 diamonds, which are the ones we're going to be talking about, are nitrogen free, and they often have top white colors as a result of this. These are strictly type 2A diamonds. There's a subgroup which has boron as an impurity. These are the type 2B diamonds, and the boron impurity gives these diamonds a blue color. They're very rare and very valuable. This is what the diamonds look like. On the left, the type 2A ones, the right, a type 2B diamond. They can be very large. The Cullinan is one of the largest at 3,100 carats, over 600 grams. They're very often irregular as opposed to the normal crystal shapes, and they can be very valuable, have very high quality. Evan Smith and his co-workers have coined the acronym CLIPPIR for these diamonds, and we are going to use this acronym in the talk. So this is what we're referring to when we talk about a CLIPPIR diamond. I don't think Evan links the blue diamonds to the CLIPPIRs, but for this talk we will. This is another example. This is the Lesedi Larona, 1100 carats, and it's from the Karoi kimberlite in the Orapa cluster in northern Botswana. Now, just something about where we find these CLIPPIR diamonds. They only common in a small number of kimberlites. These are all group 1 kimberlites. The majority of them are Cretaceous in age, and 90 million years roughly. And the majority of these Cretaceous CLIPPIR-bearing kimberlites seem to be concentrated around the margin of the Karpval craton, which is this black line. The important ones are Letseng in northern Lesotho, Jagersfontein in Jagersfontein, which produced the Yonka diamond, the 1,000-carat CLIPPIR stone, Koffiefontein, then Jwaneng in southern Zimbabwe and southern Botswana, where I happen to live, and then several kimberlites in the Orapa cluster. But they also come from the premier, or now known as the Cullinan kimberlite, which is in the center of the craton, but this is a much older pipe, 1,100 million years in age. The triangles denote group 2 kimberlites, and for some reason the group 2 kimberlites lack CLIPPIR diamonds. and they're very rare in the Lac de Gras kimberlites in Canada, and are either rare or absent in the Russian pipes. There are two very contrasting models for the origin of the CLIPPIR diamonds. We suggest that they form as part of the MEGACRYST suite in the lithosphere, and that they're young. And a more recently suggested model is that they SUB-LITHOSPHERIC, crystallized at depths in excess of 600 kilometers from metallic melts, and that they're old. Just some more background about fingerprinting diamonds. A useful fingerprint is the ratio of the carbon-13 to carbon-12, and the characteristic fingerprints for different diamond associations. Now, from a study of the inclusions in diamonds, we believe that most diamonds come from the lithosphere, and that they're associated with two main rock types, eclogites on the right. This is actually it's a diamond-bearing eclogite. These are diamonds from the Jericho kimberlite in Canada, which Katie Smart kindly said I could use. And the other principal association is a group of rocks called periddotites. The eclogites have red to orange garnets. The periddotites have mauve to lilac garnets. And on the left are histograms showing the ratios of carbon-13 to carbon-12 in these two associations. We won't go into the details of this plot, but basically on the right-hand side, these are enriched in the heavier isotope, carbon-13, and as you go across to the left, you have increasing proportions of carbon-12. And both the periddotic and the eclogitic garnets have a major peak on this heavy end of the graph at a value of -5 down here. So these are the most common diamonds. They're lithospheric, eclogitic, and periddotic. More recently, diamonds have been found with inclusions which suggest that they formed at great depth, some of them in excess of 600 kilometers. This is a phase called majorite. This is an iron nickel metal phase. These are referred to as sublithospheric or super deep diamonds. And one of the characteristics of quite a few of these diamonds, looking at the pictures, is that they often have an appreciable number of inclusions. And they have a somewhat different isotopic fingerprint, same y-axis. Collectively, they span a wide isotopic range, but at individual localities, there's a much more restricted range. Now, one of the problems in understanding the origin of the big high quality gem quality type 2 CLIPPIR stones is that at one stage there was I think a general understanding that there was a specific box that these sat in, that they were a population apart. But as we've generated more data, it's been realized that each of the different rock associations, eclogitic, periddotic, and sublithospheric, also have nitrogen-free diamonds, which by definition would be type 2 diamonds. So the question is, which, if any of these associations, is linked to the big CLIPPIR stones, the valuable stones? And this problem is well illustrated in the Cullinan kimberlite, which used to be referred to as premier, the black ornamentation denotes diamonds that are nitrogen free, in other words, by definition, type 2 diamonds. And at this locality, you get eclogitic, peridotitic, and sublithospheric stones. And these all have nitrogen free, in other words, type 2 diamonds. The bottom pane shows the CLIPPIR diamonds from this locality. These are these big, irregular, very high value stones. And Cullinan can really be considered the type locality for these CLIPPIR stones. That's where the where the Cullinan diamond came from. And the isotopic signature of these CLIPPIR stones is displaced to the left, in other words, to light isotopic ratios. So the question is, where do these fit in? Are they related to any of the three associated suites, or do they represent a distinctly different suite? Certainly looking at the isotopes, they're suggesting that they're a different population. And we think that the answer to this question lies with a very different diamond. This is something called a framocyte. We've given it the rather unkind name of the ugly duckling. And we think that this can give us insights into the origin of the CLIPPIR diamonds. These are these big, valuable type 2 diamonds. And this summarizes characteristics of these framocytes. They can be large, occasionally above 100 carats. Unlike most diamonds, which are monocrystalline, these are polycrystalline. Sometimes they're octahedral crystals lining cavities. And this is interpreted to indicate rapid crystallization of these diamonds. They may show zones of plastic deformation. They sometimes have inclusions, and these are dominantly garnet. And these come from a group of rocks called websterites, which are, broadly speaking, intermediate in composition between peridotites and eclogitic garnets, but they're calcium poor. And they appear, looking at the garnet suites in these framocytes, there appear to be distinct chrome-rich and chrome-poor suites, and these can occasionally coexist in the same diamond. And occasionally these diamonds show zoning, and where you get zoning in something from the mantle, it hasn't been there for very long. Residence at mantle temperatures and pressures will eliminate the zoning, and this suggests that these stones crystallized shortly before eruption of the host kimberlite. Calculations using rare earth elements in the websteritic garnets suggests that they could have been in equilibrium with the kimberlitic type magma. And these framocytes sometimes have carbonate inclusions, which suggests that the parental melt was carbonate rich. And very importantly, these websteritic diamonds have a very diagnostic isotopic signature. So in contrast to the peridotitic and eclogitic diamonds, which are rich in the heavy isotopes sitting around here, the websterites have compositions very much slanted towards light carbon isotope values, often with a peak around -18. And you see this both at individual localities, Joneng, Orapa, and this is an unidentified locality but believed to be from Southern Africa. So the majority of these diamonds have much lighter isotopic signatures, but in every locality, excepting Venetia, where we've only got 4 samples, but where you've got a number of samples, in addition to the light isotopic ratio diamonds, you always seem to have a subordinate population which has heavier carbon isotopic signatures. So you see that Orapa, this unidentified locality, Joneng, Venetia is the only exception, and obviously you see that in the composite. So the signature is not just a peak around -18. You have the light isotopic diamonds, but always they're associated with a subordinate group of diamonds enriched in the heavier isotope. I want to say something about megacrysts, which are simply large single-phase nodules greater than 10 millimeters. Some people want to change this to 20 millimeters, but we'll stick with 10. The most common megacrysts are garnets, pyroxenes, also olivines, and also ilmenite is a common megacryst, and occasionally zircon. But the diagnostic feature is that they're big, greater than 10 millimeters. And another characteristic is megacrysts seem to occur in two apparently discrete subgroups, which are one's chrome rich, shown by the red color, and the second is chrome poor or chrome poorer, shown by the orange. These are the garnets, the chrome rich garnets, and the chrome poor garnets of the megacryst suite. So there seem to be two subgroups to the megacrysts. And occasionally these two subgroups can occur in the same hand specimen. This illustrates a hand specimen from the Weltevreden kimberlite, described by Henry Meyer and co-workers at the second kimberlite conference. And you've got an enstatite pyroxene megacryst enclosing a chrome poor garnet megacryst, and this in turn encloses a chrome rich garnet. So the two phases coexist in this single hand specimen. There are a few other examples of the two groups coexisting, but not common. Then there's a rather unusual type of nodule which has been described in a few localities, where it's composed of pyroxenes and ilmenite, which are similar in composition to the megacryst suite, which suggests a link to the megacryst suite, but they have this a circular needle-shaped habit, and this is interpreted to suggest rapid crystallization. These are rapid quench textures, basically, but the compositions seem to link this group of rocks to the megacryst suite. Just to summarize some of the important characteristics of megacrysts: large. There's a subset that shows evidence for rapid crystallization. Chrome rich and chrome poor suites, which occasionally coexist in the same hand specimen. And again, using rare earth elements, it's been suggested that the chrome rich garnets could have formed in equilibrium with the kimberlitic type magma. The zircon megacrysts have young ages, very close to the age of the host kimberlite, and this suggests that the megacrysts formed at the time or just prior to kimberlite eruption. And there are a number of other lines of evidence that support this. So the megacrysts sometimes show deformation textures, and some of them have carbonate inclusions, suggesting that they come from a carbonate-rich magma. And if you compare megacrysts and phragmicites, there are remarkable parallels, both in the age, the textures, and the occurrence of chrome-rich and chrome-poor suites. And I think you can only draw one conclusion, is that the phragmicites and the megacrysts are linked. At least that's the way it seems like to me. And this is underlined by the composition of the megacrysts and the the Websteritic garnets. The blue are Websteritic garnets from Venetia. The blue line shows the range in Websteritic garnets from the unknown locality, but presumably in southern Africa. And the orange symbols are megacrysts from a number of different localities. And there's a strong overlap between the field for the Websteritic garnet inclusions and the megacrysts. And with the other similarities, I think there's only one conclusion that we can draw, and that's that the megacrysts and the Websteritic bearing suite are part of the same population. Or looked at differently, the Framosite ugly duckling is a megacryst, and certainly the size is megacrystic. But this has an important spin-off, then that is that the megacryst suite must now be acknowledged as a distinct diamond paragenesis synonymous with the Websterites. There seems to have been a lot of resistance to this idea of the megacrysts being a diamond-linked suite, which I've never understood. It's that they carbonate-rich fluids, and that seems to be a good fluid to turn into a diamond under the right conditions. And just to remind you, these Websteritic or megacryst diamonds have a very distinct carbon isotopic signature, different from the associated or from the eclogitic and the peridotitic suites. And that gets us back to looking at the big CLIPPIR diamonds and looking at what the Websterites are telling us about them. And just to go back to the type area, Cullinan, where the CLIPPIR diamonds at Cullinan have this very distinct light carbon enriched signature, very different from the associated SUB-LITHOSPHERIC, peridotitic and eclogitic suites. But if you compare it to these are the Cullinan diamonds, the blue ones are symbols of blue diamonds. These orange symbols are composite samples. Between the three of them, they represent 30 different diamond fragments. And these are the Framosites down here. The orange ones have inclusions of Websteritic garnets or Websteritic inclusions. And you can see that the CLIPPIR diamonds at Cullinan cover the same range as the Websteritic suite. And just like the Websterites, there's a subordinate population. This is an absolute characteristic of the Websterites, it seems, this subordinate heavier isotopic composition. Then these are the CLIPPIR diamonds recently analyzed from the Letseng kimberlite, another important CLIPPIR producer, one of the most important ones perhaps. And again, they show this range in isotopic signatures biased towards the light isotope, carbon 12. And just like the Websteritic suite, there's the subordinate heavier isotopic subpopulation. Now, just to put this into perspective, prior to the publication of this data, these diamonds were studied and they were found to contain metallic inclusions. These are super deep or sublithospheric diamonds. And these are nitrogen-free diamonds again, so they type 2 diamonds, and these were used as evidence to suggest that the CLIPPIR stones had a super deep origin. Now, there are only 6 of them, so statistically you can't say anything about it, about this population, I'm told by the statisticians, and I go along with that. But I think you have a major problem suggesting that these diamonds are representative of the associated clippers. You'd have an equal problem proving that they were different, I guess, but you certainly would have a problem trying to say that these are representative of this suite. One of the other important clipper producers is Orapa. Orapa is a major producer of framocyte diamonds, by the way, and these were inclusion-free ones, but the composition is similar to the framocytes elsewhere, mainly light isotopically enriched, subordinate heavy isotopically enriched composition. And then you get the Websterites, and this population has a very similar signature to other Websterites. And at Orapa, a number of irregular type 2 stones which didn't have inclusions. Which ones would these be? These ones up top here with the cross hatching. These are nitrogen free, in other words, type 2 diamonds, but described as irregular shaped, and they plot in this Websteritic population. Then also there were a group of very strange nitrogen-free diamonds, also described as irregular, but grey. They didn't classify them, or the study didn't classify them according to type, but they also plot in the Websteritic field. So Orapa, another important clipper producer, has a Websteritic suite that includes irregular shaped diamonds. All of these stones, of course, were very small because De Beers didn't see fit to give samples of the true clippers for investigation. Just to remind you of the carbon isotopic signature of the sublithospheric diamonds, a wide range, but at individual localities, a much more restricted range. And this is summarized in this table, and at all of the localities where sublithospheric diamonds have been recovered, the range of those diamonds, even where you've had a significant number of grains analyzed, 16 in Cullinan, 19 in Jagersfontein, show a very restricted range in delta 13 C units, whereas with the framocytes and the clippers, you have a much wider range. And of course, the framocytes and the clippers have closely overlapping ranges in carbon isotopic signatures. And I think if you put these similarities together, the clippers have a wide isotopic range that overlaps the Websteritic range. The associated sublithospheric or super deep diamonds at both Letseng and Cullinan have a very restricted range, and it differs from the associated true clippers, and the same is true at Orapa. The Websteritic diamonds have a wide range, and at Orapa they haven't described a super deep suite. And I think if you look at the similarities in isotopic signatures of the clipper diamonds and the Websterites, I think it's very difficult to come to any conclusion other than that the the CLIPPIR diamonds have a Websteritic paragenesis, and in fact, in the study of the CLIPPIR diamonds from Letseng, Annetta Bunnis and her co-workers suggested that these were either, how did they put it? They were eclogitic and or Websteritic in association. So if they're Websteritic, they must also be megacrysts. So just to summarize, the similar isotopic signatures of the CLIPPIR diamonds and the Websteritic diamonds, I believe, is a very strong link to the megacryst suite. And just in case you don't believe me, this just illustrates that the CLIPPIR diamonds are actually megacrysts from a petrographic point of view. Now, this will probably be a little bit controversial, but this is how I see megacrysts forming, and it really follows on a model proposed by John Gurney and Ben Harte. And at Monastery and Jagersfontein, these arrows show the conditions at which megacrysts form, and at both localities they formed over a very restricted depth range or pressure range, but over a wide range in temperature. So to explain the origin of these rocks, you need a model that will give you a wide temperature range at a single pressure. By the way, an important curve is this graphite diamond inversion curve, and up here you get graphite stable, down here you get diamond stable, and you can see the megacrysts at Monastery extend from the graphite stability field down towards the diamond stability field, and the Jagersfontein suite, which formed at slightly higher pressures, their crystallization range extended into the diamond stability field. And to explain this, this is a modification of a model which Ben Harte and John Gurney put together, and which I have always thought was an extremely elegant model. We've perhaps modified it slightly in terms of what the magma was, but what they suggested was that the megacryst suite formed within the thermal aureole surrounding a magma body in the mantle, and that small volumes of this magma body were injected into surrounding fractures, and that the megacrysts formed down this thermal gradient as basically pegmatites, similar to pegmatites surrounding a granite batholith. They were, in this paper, they were silent on the nature of the parental magma. We believe it's the kimberlite, but that actually isn't critical for the model. But the important thing is that over a relatively small depth range, you had a wide temperature range. And you'll recall, if we go back, that the lower temperature part of the range in this thermal aureole was getting close to the diamond graphite stability field. And we suggest that the big CLIPPIR diamonds formed as part of the megacryst suite at the low temperature extreme of the range in the outer parts of the thermal aureole, where temperatures were cool enough. Then Dan Schulze way back pointed out that at the temperatures that the megacryst would have formed, the parental magmas wouldn't have crystallized completely. So you'd have had small residual volumes of residual evolved magma, shown by these little blue blobs. And what we suggest is that at the time of eruption, eruption is probably preceded by fracturing of the mantle, and these residual liquids might have lost volatiles, might have cooled against colder surrounding mantle, and the result would be that they would have quenched very rapidly. So we suggest that quenching of these liquids would have produced the ugly duckling, the phragmocytes, and also these nodules with the quenched textures. So we suggest that these all formed in the associated with some or other magma body. We believe the kimberlite, but that's not critical to the model, over a limited range of pressures. One of the things that one has to explain is the isotopic signature of the CLIPPIRs and the phragmocytes. And carbon, if a magma is crystallizing and evolves CO2, the heavier isotope is going to be partitioned into the CO2 preferentially. So with crystallization, the residual magma will become enriched in carbon-12, the light isotope. So as the megacryst suite crystallizes down the thermal gradient in the thermal aureole, it'll become progressively more enriched in carbon-12. Now, this is very much work in progress, but just some pointers as to what I think one needs to do to try and find some sort of proxy to work out whether CLIPPIR diamonds might be present in a kimberlite. At the moment, the only way to test for them is a costly bulk sample. So it would be very nice to get something equivalent to G10 garnets that could give an estimate or an indication that there could be CLIPPIRs in the kimberlite. And I think the MEGACRYST suite is probably going to be the way to go, or understanding the MEGACRYST suite is the way to go. And just to illustrate the sorts of things that I think could be useful, this diagram shows garnet megacrysts from Monastery, which is a group 1 kimberlite, and the group 2 star kimberlite. These are the star garnet megacrysts. And at Monastery, they show a wide range in compositions down to very low magnesium numbers. And in the group 2 kimberlite, for whatever reason, is a much more restricted range, and you don't get down to the same low magnesium numbers. Now, in very crude terms, your magnesium number is a proxy for temperature. So this is indicating that you're going from left to right, lower magnesium number to lower temperatures. And so what this is suggesting is that at Monastery, crystallization of the megacrysts, or at least the garnets, extended to lower temperatures. And in other words, that at Monastery, which in fact produces CLIPPIR diamonds, not very many, but it's produced at 200 carat stone, that your crystallization went to temperatures that could cross this graphite diamond inversion curve. But with the group 2 kimberlites, for whatever reason, crystallization was arrested at higher temperatures, and they never got into the diamond stability field. And similar reasoning, I think, explains the rarity of diamonds in Lac de Gras and the Russian kimberlites. I don't have Garnet's megacryst data for these pipes, but olivines can tell a very similar story. The important aspects of this plot are these crosses, and they simply show the composition of edges of all olivines. These are them here. This is from the Leslie kimberlite in the Lac de Gras cluster. This is the group 2 Newlands kimberlite in South Africa, the Finch kimberlite, and Udashnaya East in Russia. And in all kimberlites, there seems to be a subordinate population of olivines which are iron-rich relative to the edge compositions. Here they are from Udashnaya, here in Finch, here in Leslie in the Lac de Gras kimberlites, and here in the Newlands kimberlites. And I think I've always argued that these olivines are part of the megacryst suite, and I think that's now becoming fairly well established. And so these are basically the megacrysts. And at these localities which seem to lack type 2 diamonds, the megacryst compositions go down to a little bit above a magnesium number of 84. If you go to Letseng, which is an important producer of these CLIPPIR diamonds, here the edge compositions again, these are the iron-rich olivines linked to the megacryst suite, and we're going down to much more evolved compositions down below 80. In fact, if you look at the true megacryst from this locality, sorry, at Monastery, they go down to even lower magnesium numbers. Again, the magnesium number is a broad proxy for temperatures, and so at Letseng, it looks as though the megacrysts continued crystallizing over a wider temperature range and down to temperatures that would have got into the diamond stability field. So this is Monastery, and what we're suggesting is you have something similar at Letseng, that you crossed over the graphite diamond inversion curve, but that in the Lac de Gras, the Russian and the type 2 pipes, for some reason, megacryst crystallization stopped earlier at higher temperatures in the graphite stability field. So I think the megacrysts provide an indication of why CLIPPIRs are absent in some kimberlites. This is not particularly useful. What we really want is something to predict the presence of CLIPPIRs. This is something we're still thinking about. We haven't cracked this, but we believe that the key to refining this is that we need to refine our understanding of the megacryst suite. But of course, if you can link the presence or absence to the megacrysts, or at least the absence to the megacrysts, this is a strong line of support for our model that these CLIPPIR diamonds are part of the megacryst suite. Now, just a few words of some of our concerns for the alternate model, the CLIPPIR model, which I think is, well, I know has much wider support, but we feel that there are a number of problems. Now, when this model was developed, diamonds were found with sublithospheric inclusions, including a large number with metallic inclusions. These were nitrogen-free diamonds, so by definition they were type 2, and it was inferred that these nitrogen-free diamonds were linked to the clippers. But if you want to use such inclusion-bearing diamonds to understand the clipper diamonds, we think there are two things that you have to do. And the first is to demonstrate why the inclusion-bearing stones differ from known parageneses. And secondly, even if they do differ from known parageneses, why they might be linked to the clippers. And in these diamonds which were used to infer a link to the clipper diamonds, the main inclusions were metal carbides, a mineral called brayite and another one called margarite. These are all sublithospheric minerals. But these phases have all been reported in the Juína alluvial suite in Brazil. And one of the features of these sublithospheric diamonds that were linked to the clippers is that a large number of them had hydrogen impurities. And hydrogen impurities is one of the characteristics of the sublithospheric Juína stones. So we think that there are very strong similarities between the inclusions in the diamonds inferred to be linked to the clippers and sublithospheric diamonds that have been reported at other localities. But even if this is not the case, so we're not quite sure why these should be different parageneses, but even if they are, why should they be linked to the clippers? And we think this is a problem that needs to be explained. And this is highlighted by data which I showed previously. These were diamonds, sublithospheric diamonds with metallic inclusions from Letseng, and inferred to be linked to the Letseng clipper diamonds. But this is data published subsequently for the Letseng clippers, and I think it's problematic to suggest that these stones are representative of the suite down here. Certainly not isotopically representative, but it's a small population. So I think at Letseng, to resolve this issue, a larger number of sublithospheric stones need to be recovered, and so we can get a better definition of the carbon isotopic signature. Then another difference we see between these inclusion-bearing sublithospheric stones and the clippers is that many of them seem to be quite rich in inclusions, and the clippers by definition are inclusion poor, and this underlines the problem of why should these be linked to the clippers. And sorry, excuse me. And then of course at Cullinan, where you've got a statistically reasonable number of sublithospheric stones, they're very different from the associated clippers. And this suggests that certainly at Cullinan, the sublithospheric, the super deep suite, don't have anything to do with the clipper diamonds. And this data, we should point out, was also published subsequent to the original science paper suggesting a super deep origin for the clippers. So we think that recent data is just not supporting the original super deep model for the sublithospheric diamonds. And just to underline this, at Cullinan, the phases in the super deep diamonds include this perovskite structured pyroxene composition, which suggests that it's come from very, very great depths. And in fact, the only unreverted example of unreverted CAPV is from Cullinan. They're margarite diamonds. They're also eclogitic diamonds, and they're also peridotitic diamonds. So Cullinan has sampled a wide range of the upper and lower mantle, stretching from the lower mantle through the transition zone and into the lithosphere. Then there's another general problem. CaSiO3, which at surface temperatures and pressures is wollastonite, occurs in 3 different polymorphs. There's one which has now been renamed brayite, which is this one over here, which was originally referred to as CaSiO3 wallstromite. And then there's a very high pressure form with a perovskite structure, which comes from the lower mantle. And one of the fairly common inclusions in diamonds which have been interpreted to be super deep is brayite. And it's generally assumed that if you find, or many people have assumed that if you find brayite, that this is in fact this deep phase that's inverted at shallow pressures. But this brayite, the intermediate pressure polymorph, is actually stable in its own right over a wide pressure range, stretching right into the lithosphere. This would be the base of the lithosphere. And particularly in carbonate-rich magmas or environments, brayite can crystallize at lithospheric depths. And there've recently been a number of papers that have they've just come out, pointing out that you can't use brayite on its own to infer that the diamond originally came from the lower mantle. And that's a fairly general problem with not only the CLIPPIR problem, but looking at lower mantle diamonds. So this is just a summary of what we see as some of the problems with the super deep model for the CLIPPIR diamonds. And I think we leave it at that.
Thank you, Andy. That was most interesting, and I'm sure we're going to generate a lot of discussion on this. Folks, please, if you want to ask a question, feel free to raise your hand. You'll see at the bottom of the list of participants, there is a little blue icon. Just click on that and you can raise your hand. Dave, would you like to unmute yourself and ask your question, please?
Hi, thanks a lot. I don't know if you want me to put my video on. Yeah, thanks for that, Andy. That was an amazing talk. And as you know, I've been following your work for many years now. To get away from what we started talking about is our conceptual idea of where diamonds came from. And we go back to the mid-80s, early 80s, when in the De Beers school, at any rate, all diamonds were old and xenocrysts. So that was the story. It was the old story about the train. The kimberlite was just the train, and as it went along on its way, it picked up new diamonds on the way at the stations, on the way to the surface. I think that perception has really changed our ideas with regards to diamonds, and we're seeing all kinds of different diamond parageneses here. Just carry on a bit. Your whole megacryst crystallization is phenomenal, and it would be wonderful if people would come up with megacryst crystallization progressions to try and understand.
Then you can talk in if you want. Oh, okay.
Sorry, can I carry on?
Yes, go ahead.
So the work on the megacrysts, and I believe that could be a useful exploration tool, has still got a long way to go. I could probably carry on for a long time on this topic, talking about carbon 12-13 ratios. It's like we talk about carbon 12 as the light one and carbon 13 as the heavy one. It gives you the wrong ideas of these things. In fact, carbon 12 is a bit of a laggard, and carbon 13 is, as you showed, is much quicker to go into the melt or to fly away up into the lithosphere. You talked about the group 2 kimberlites and their role. I think what happened there is they merely exploded before they got to the point of generating and growing good CLIPPIR diamonds. I think another point to make is this whole progression towards iron-rich an iron-rich environment, and that seems to me to be one of the keys. I could talk largely about calcium SiO3 and Briat. If you looked at that diagram of yours, the TP diagram, you'll notice that on the temperatures, the temperatures started at around about 1200 degrees centigrade, and the curve at that point is at 300 kilometers. So actually, if you move the temperatures down a lot, you could actually put the Briat or even the perovskite structured CaSiO3 into much shallower environments. And just to support that a little bit, you did mention the zircons, the megacrystic kimberlitic zircons. I don't know if you've looked at it, but there was a titanium thermometer, and you've actually almost referred to it indirectly, which says that these zircons crystallized at the time of eruption, and that they were very cold, like 650 degrees to 700, and certainly under 1,000. So I'll just leave you with a lot of those things, and thanks very much for your contributions. It helps explorationists make a little bit of a move forward.
Yeah, thanks, Dave. I think the megacrysts are starting to get much more attention these days. You're seeing more and more papers on them, and I think that's a great development. And I think, you know, understanding them is going to be one of the keys to understanding where you find clippers.
No, absolutely. Maybe one of the things that I did talk about when I gave a Zoom meeting back in May was the use of the microdiamonds, the type 2 or nitrogen-free microdiamonds that Steve Haggerty has been talking about recently, the ones he refers to as the microsensor stricter MDS, I think he called them. And I've been quite interested in the role of those grains, which is another type 2 genetic variety.
Yeah, no, I agree. I think that was a very interesting paper, Dave. And I think there's a lot in that we need to think about.
Yeah, thanks, Andy. Good work.
And Andy, we have a question on the chat line for you. What do you think makes these megacrysts to be highly irregular in shape?
Well, the standard explanation is that they've been resorbed. I'm not sure that that's the full answer. If you look at pegmatites, granite pegmatites, and sometimes the minerals like beryl in a pegmatite makes beautiful crystals, but the quartz and the feldspar are often very irregular, and I have a suspicion that that part of the irregularity is simply a growth feature, but that's a feeling. I don't have any firm answer on that.
Thank you. Is there anybody else who would like to raise a hand and ask a question?
Craig here. Andy, you said early in the lecture that these CLIPPIR diamonds tend to be restricted to type 1 kimberlites, group 1 kimberlites. Is that also true of the Framasite?
You know, I don't know the answer to that, Craig. Certainly, Orapa is one of the important producers. It's as is Jwaneng. You'd have to speak to someone like Jim to find out if he's seen them in any group 2 kimberlites, but I don't know of any. They've certainly been described in localities that have produced clippers. I think Jwaneng's also a Framasite producer. Do any of the De Beers people know?
Okay, Norman, would you like to ask your question, please? Don't forget to unmute yourself.
Is that on? Yes, I think that's unmuted myself. Hi there, Tanya. Hi, Andy. Look, you know that I'm one of your long-term major supporters. And you know that I did my PhD on Letseng, and that you've used some of the data from my work at Letseng in some of your earlier work on MEGACRYSTS and their relationship into, I forget that paper. It was relationship to the sheared peridotites, wasn't it?
That's right. Yeah.
Yeah. So I'm a great supporter, but I'm completely out of touch. Well, not completely, with all the chemistry, the wizardry that you've got there. But one area that I keep wanting to try and push with you and now in this forum is that it's quite obvious that the space considerations of the veinlets around the rising diaper and the thermal aureole to the kimberlite are plenty large enough for the crystallization of large crystals in whatever form. And the evidence for that is patent in the size of the megacrysts themselves. So if the chemistry supports a diamond growth in that environment, then it's obvious that diamond crystals in those veinlets have the potential to be very large because there is no constraint from solid rock around them. They are in a crystal mush. If we go down to the other model, which is flawed, and I don't know whether it's clear, the CLIPPIR definition is not Andy's definition. It's the definition of the people who are talking about diamonds at 600 kilometers depth. And their definition says that they're inclusion poor, I think is that the phrase. And
Yep.
yet, you know, Andy showed one of the slides that shows these diamonds that are full of inclusions. So their definition is flawed. But the point I'd like to come to is that what they're saying is that there are diamonds that are crystallizing in a liquid metal melt at great depth. Now, I want to ask the question because of space constraints. You know, how big a space do you, Andy, think that those metal melts might be? And the obvious follow-up is, you know, are they large enough melt portions to host the crystallization of not the small type 2 diamonds, but the large type 2 diamonds that we get at Letseng and Cullinan and elsewhere?
Yeah, I don't know the answer to that. The assumption is that they are large enough, and in fact, one of the points made in that science paper was that crystallization in a liquid would allow just what you are referring to, a lack of constraint. So, but I haven't been down there, Norman. So I think they envisaged that they were large enough to allow, you know, a large crystal to form. I think that was part of the model.
But that is a fundamental assumption that they're making that maybe is not supported by any real science.
No, I mean, that's a very important paper because, you know, my understanding is that they recognized a large number of metallic inclusions when they realized that they were masked by graphite, and an expansion of the graphite generated secondary carbon. Most people didn't look into the graphite, but when they did that, they found there was a lot of iron around, and that's a very important contribution, irrespective of whether they link to the CLIPPIRs. And Evan Smith, in his recent talk, discussed an inclusion-bearing sublithospheric diamond that was, I think, 140 carats, and that must be the biggest sublithospheric diamond if you exclude the true CLIPPIRs, the inclusion poor suite. So the question is, how did those things get to the surface? I think that's a major question that we have to answer, and something that we need to understand, irrespective of the origin of the CLIPPIRs. You know, how do you get these sublithospheric diamonds to the surface? And so that paper raises a lot of very, very important questions that we still need to address, quite apart from the question of whether the inclusion bearing stones were CLIPPIRs or not.
Well, if we're looking at the two situations that go back up to your thermal aureole, the analog of you know, masses of metal melts in those deep diamonds ought to be masses of little bits of kimberlite melt in the big diamonds in the thermal aureole, which of course you don't find.
Yeah, you know, I'm obviously biased. I prefer the MEGACRYST model, and but certainly the data that's been produced on these sublithospheric diamonds has been a major game changer, and it you know, it raises a lot of questions. How big were the melt volumes? So it raises an incredibly important group of questions that have to be answered.
I've taken a lot of your time, as you put that wonderful graphic of the thermal aureole back on. If anybody has any doubts about that, you know, I've got a couple of comments I would make that relate to my work at LETSEC, but let me give the floor to somebody else at this moment.
Norman, we're going to invite you back to give a whole presentation by yourself. So don't go too far away. Dave, do you have a short question to ask? Dave, you can unmute yourself and ask a quick question.
You mean Dave Cornell?
No, it's me, Dave Apter.
No, Dave Apter had his hand up.
I was just going to make another comment when you're talking about sublithospheric diamonds, and it's not only 600 kilometers down, well, I think it's deep primewood, but it's also further down towards 2,900 kilometers on the deep D double prime boundary, where you find, and some people have suggested these diamonds grew down there on the core mantle boundary almost. My question is, does Clifford's law still apply? If you're bringing diamonds up from those sort of depths, what is the role of a craton, which is only about 200-300 kilometers thick? You know, does it act as a magnet, or what happens? Thanks.
Can I pass on that one, Dave? I mean, these are important questions, but I don't.
Yeah, no, absolutely. It's just one that I can't figure out, because, you know, maybe if we're really looking for clippers, and I'm an exploration geologist, I would suggest maybe the Hawaiian Diamond Exploration Company, a nice place to put an office.
All very interesting comments, and I'm sure we're going to generate a lot of offline discussion on this, and Andy can come back and tell us about some of the results he's obtained in a year or so. Are there any other questions? Short questions, just to keep within our time. Going once? Going twice? Sold to the man in the hat. Thank you all very much for coming for our lunchtime lecture. Andy, thank you, and Herb very much. I look forward to hearing more about this in due time. And once again, thank you to Pitto Associates for sponsoring this month's lunchtime lectures. And with that, thank you all and goodbye.
Cheers, Tanya. Thanks very much.
Thanks, Andy. Thanks, everybody.
Yeah,
Thanks so
cheers,
much,
everybody.
Andy and Herb.
Craig, you can end the meeting for everybody, please.
Okay, I'll do that now. Thank you very much all.